Hi, everybody. Welcome back to Dave's Math channel. This is my continuing feature on the Math Lovers book. And I'm continuing my subseries on computational complexity. This is part of section 8.5. Actually, it's all section 8.5, chapter 8, which is on computation. And today I'm going to talk about a very important type of notation in computer science called Big O notation. So, anyway, let's begin. So, first, I have to tell you what Big O notation is. So, we say that a function. Forget about things like running time. It's used for things like running time and memory. But right now, let's just think about functions. And this is used in math as well. It's primarily used in computer science, but it's also used in analysis and math. So suppose we have some function, univariate function f of x, and we say that f of x is big O of g of x, where g of x is another function. What we mean by that is that for every value of x, we can bound f of x by some constant times g of x. And usually g of x is a pretty simple function. Like, for instance, g of x could be a constant. In that case, we'd say O of 1. And a good example of functions is O of 1 or sine and cosine because they're bounded between 1 and minus 1. So they never get bigger than 1. And linear functions are O of x. And let's just do a couple examples here because I think it's better to look at some examples. But suppose we have the function f of x equals x. That's a very simple function, just a straight line with slope 45 degrees on the xy point. And clearly f of x is big O of x. So the reason it is because x is bounded by just x itself, kx, where k is 1. So remember that we say f of x is O of g of x of f of x. The absolute value of f of x is always less than or equal to k times g of x, the absolute value of g of x, for every for some constant k. So for that's clearly true for f of x equals x. What about f of x equals cx, where c is a constant? Well, it's still O of x because we don't care about the constant. So the constant is kind of taken care of in the big O notation. We don't care what constant's in front. It's still bounded by a linear function of x, namely cx itself. So these are two pretty trivial examples. Now I'll do a little bit harder ones. What about a more general linear function like f of x equals ax plus b? This is a general equation of a straight line, a function whose graph looks like a straight line as long as it's not vertical. So it's a function. Vertical line is not a function, but every other function that's linear looks like this, ax plus b. Well, it's still O of x, and the reason it is because if for sufficiently large x, ax plus b is less than or equal to ax plus bx. When x is big, x is going to dominate, and we can write that as a plus b in parentheses times x. So our constant k is just a plus b. So since we found a constant times x that bounds f of x, we say again f of x is big O of x. So far, all three examples I've given are big O of x. Well, I'm going to finish with an example that's not big O of x. This was big O of x squared. What about instead of a general linear function, we have a general quadratic? You know, ax squared plus bx plus c, where a, b, and c are arbitrary constants. And we want to show that this is big O of x squared. Well, same idea. We just take a large value of x, and if x is bigger than 1, then ax squared plus bx plus c is less than or equal to ax squared plus bx squared plus cx squared. Here I'm assuming a, b, and c are all positive, otherwise you have to take their absolute values. But then you can just factor out the a plus b plus c, make that our constant k. So we see this bounded by another constant k times x squared. So this time we say f of x is O of x squared. And in general, if you have a polynomial, I may as well cut to the chase here with polynomials. if f of x was a polynomial of degree n, then it turns out that f of x is big O of x to the n. So, polynomials, you probably learned this when you were learning about polynomials in high school. Polynomials grow faster the bigger their degree. I think you guys know that. I mean, a straight line doesn't grow very fast. It just has constant slope. But a parabola, which is quadratic, that grows like x squared. And you can see it arcing out pretty quickly. And x cubed grows even faster than that. X fourth grows even faster than that. So in general, the bigger your power, the bigger your degree of your polynomial, the faster it grows. But these are what are called polynomial. I mean, when we're talking about running time, I've got to come in the chase here. I'm skipping ahead a little bit. Next time I'll talk about polynomial and exponential growth. A polynomial, we say that an algorithm is a polynomial time algorithm. Usually those are called easy algorithms. This is kind of a standard. Um, and a polynomial algorithm is just an algorithm that runs in polynomial time. In other words, its running time is O of x to the n for some finite exponent. So that's what we mean by polynomial time. And if it's slower than polynomial time, we say it's exponential time. Those are hard. Anyway, that completes my video for today. Thank you for watching. Long live math, and I'll see you guys next time. Bye.